All right, welcome back from the break. I'd like to introduce our next speaker, is Bob Carpenter. And Bob got his degree in computer science and cognitive and computer science from University of Edinburgh. And he's been at Carnegie Mellon and is recently at Columbia University in the Department of Statistics and is part of a company called LingPipe, which most of us in this room know about. And we're really looking forward to your talk.
Thanks. Thanks for keeping the introduction short. So what I'm going to talk about in general is statistical models for data annotation, and I'll make it a little clearer as I go along exactly what that is. I think everybody in this room knows why we want to annotate data, but I just want to review because it's important, because I think there's two different reasons why we want to annotate data. One is that we want to create some kind of gold standard corpus in which to evaluate some system. The system we evaluate may not be probabilistic or may not be machine learning driven. Or we want to build a corpus to evaluate, to build or estimate a statistical model. That is, we don't really care about evaluation so much. We just need some data to get a system off the ground. And those will lead to different decisions as to how you're going to spend your effort in your corpus. If your goal is just to build the best classifier as opposed to build the best corpus, right? Those are two very different goals in terms of what error rate, say, you're aiming at, because many learning systems are noise tolerant. So the other reason to annotate data, besides the first two, to estimate a model or evaluate a model, is to evaluate the coding standard. So very typically, you're in a situation where you're trying to say, I have an idea of some information I'd like to extract. Is that even possible? Can I get some humans to do that? Is my task well enough defined? Can I get some humans to do it so that they agree that I'm confident what I'm trying to do even makes sense before I try to build a system? So the traditional approach to data annotation, although we've already seen a couple non-traditional approaches already here today, is to develop or revise a coding standard, then annotate the data with multiple annotators, evaluate inter-annotator agreement, analyze and adjudicate any kind of disagreements, and keep doing that until you converge, right? It's very important that when you analyze and adjudicate, that you then go back for another round of annotation, because the analyzing the data and adjudicating has basically changed your coding standard. So to be confident in the traditional way, you need to repeat this again with more data. So then, very often what we want to do is we've done some annotation, say, using that traditional method, and then we want to move from the data that we have annotated over to some kind of gold standard, right? So often what we're going to do is, in this situation, multiple annotators may have disagreed on data. So typically we'll solicit some kind of adjudication judgment. The problem is that third judges or fifth judges or whoever's coming in to break the tie may not agree. There may still not be a consensus. And as I said before, the changes to the coding standard requires new eval data. What's surprisingly common in a lot of these domains is to just censor the data items. So for instance, the biocreative named entity data set, they had two annotators. In cases where the annotators didn't agree, they just threw the data out. That, of course, leads to the obvious bias in evaluation that the instances that are hard, Lynette, is that not what they did? Okay. I thought I was reading that's what they did. Okay, I'll have to go look that up. Maybe I'm thinking of something else, or maybe I'm just hallucinating. But it's actually a very common approach. In fact, there was a CompLing paper arguing that this was desirable because you wanted only high-quality, clear items in your data set. So I'm not imagining the overall problem, but maybe biocreative didn't do that. In terms of the coder accuracy, just some simple statistics. If you've got 80% coder accuracy, which is usually pretty good in these kinds of tasks, that's going to yield a 4% error rate with double annotation, right? You see this in something like the RTE data set, which use double annotators. They have about a 4% error rate in RTE1. Even if you have 90% accurate annotators, which is pushing the bounds of what you can do with natural language data, it's still going to yield 1% error in your data set. You look at things like the Penn Tree Bank, and they think they're estimating around 1, 2, 3% error in the actual coding. Part of that's just the coding standard's not real clear about particles and prepositions. So the problem is here, you can't infer the corpus accuracy without more work, right? None of what I've told you here tells you, unless you know what the accuracy of the coders are, you don't know what the accuracy of your corpus is. So another very common technique in corpus development is to bias the category counts to achieve what people call balance, right? So you wind up with a very skewed corpus. It may be something like 5% positive and 95% negative in real-world data, but for the sake of NLP evaluations, everybody makes it 50, not everybody, but it's very common to make it 50-50, and you have to be careful about what you're doing because that evaluation is not going to be representative of the real-world task. So I want to go on a couple slide rant about kappa statistics. Kappa statistics are the industry standard for evaluating inter-annotator agreement, at least I think in the present day that's still true. Kappa attempts to adjust for the difficulty of the task. So kappa is defined as the agreement rate that a pair of annotators actually show minus E, which is the expected agreement rate, divided by 1 minus the expected agreement rate. Right? You wind up with a different set of kappa. There's different notions of kappa based on how you define chance agreement, but it's all done independently of the actual items being annotated. And then usually some sort of like p-values, some arbitrary threshold is set, and kappas above that level are considered acceptable. So the problem with kappa is that it just gives you a pairwise measure over shared annotations. Very often you have the data that you collect doesn't look like every annotator annotated the same subset of data. So if you're doing something like on the Mechanical Turk, you might get 100 annotators, each of which is annotated 5% of the data, and many pairs of those annotators don't even overlap. The real problem, though, is that kappa is really useless for inference. It doesn't predict the corpus accuracy, and it doesn't predict the annotator accuracy. Those are the two things that we really care about, right? And kappa doesn't tell us anything about either of those, although it's correlated. I shouldn't say it doesn't tell you anything. High kappa tends to mean that you're going to have a better accuracy on both counts. Another problem with kappa is 2 wrongs make a right. Right? So annotators with 10% accuracy and annotators with 90% accuracy are going to have exactly the same agreement and lead to exactly the same kappa scores. Right? The problem is that the 10% accurate annotator disagrees all the time. So you can think of a degenerate case of this. Say 2 annotators always return 1, a kind of common trend on something like Mechanical Turk. Those annotators look golden from a kappa point of view because they have 100% agreement, but they're wrong almost all the time. Right? In the other direction, kappa reduces to agreement for hard problems. So as the expected agreement goes to 0, kappa just becomes agreement. Overall, I think agreement's more relevant to report than kappa. Kappa can be 0 even with high accuracy if there's a low or a high prevalence. So for instance, if there's a 5% positive prevalence of items in the data and the annotators are 95% accurate, kappa is going to be 0. Right? This is a case where the annotators are actually really good. The data is going to be really good that you get out, but kappa makes it look really miserable. Other problems with kappa have to do with the assumptions underlying the modeling. It assumes all the annotators have the same accuracies. It assumes the annotators are unbiased. If the annotators are biased the same way, like they always return 1, then kappa gets estimated too high. All the errors for the categories have the same importance, so it's very common that you have low prevalence in a task of positive categories, very high agreement on the negative categories, but it's then very common at the same time to value true positives and not want false negatives in an application, and all this sort of comes together to mean that kappa is not going to work real well. Kappa is typically point estimated without uncertainty. Right? This doesn't need to be done. You can do a bootstrap or something and put confidence intervals around your kappa. People are often estimating kappa with very small amounts of data that leads to very high, wide confidence intervals. And another key thing that I'm going to get to later is the kappa assumes annotations for items are uncorrelated. I assume a lot of people in this room have actually annotated data and are familiar with the phenomenon that some items are harder to annotate than others. Right? So there's definite effects of the item. You see this in just about every corpus I've ever looked at. So now I want to change gears to the main topic, now that I've dismissed kappa, to more generative models of the annotation process. And interestingly, these go back to really the mid-'70s, but I think the seminal paper in this was Dawid and Skene's paper in 1979, and I'm going to tell you what their model does and why I think it's better than using something like kappa. Right, so we start with some kind of generative story for the categorical annotation. So what we're going to do, right, I'm a Bayesian statistician, so I'm going to build a full generative model of the entire data generation process from top to bottom. Right? So this is going to be a model of not only how the corpus gets created, but how the annotations get created. So the first thing we have to do is we have to find the distribution of categories. So I'm going to use pi for that. And I'm assuming just a simple categorical where there's a finite number of categories. This can all be generalized to continuous things or ordinal things. There's a ton of literature on these kinds of models in the epidemiology literature where they use them to investigate clinical tests like blood tests or saliva tests or doctors giving exams. In fact, I should have said that Dawid and Skene actually built this model. I say this actually later. Well, I'll come back to it and say it later. So the first thing we estimate is the probability of each category, right? So this is going to say what's the distribution of category labels in the data, which is getting back to, say, the kind of thing that Charles was trying to estimate in the previous talk. Then what we're going to do, and that's going to be based on some prior alpha. That's just a fixed hyperparameter here for the time being. Then what we're going to do is we're going to look at the true category of item I. So we have a bunch of items that we want to annotate, indexed by I, and then we're going to say the ith item gets an index based on that distribution of category. So far we haven't got any annotation or anything. Those first two lines just generate the corpus. So now we've got the corpus, a labeled corpus. Right, now we look at annotation. Well, what we're going to do for annotation is we're going to assume that each annotator, J, we're going to index the annotators with J and the categories with K. What we're going to say is that for every category K, each annotator is going to have a response. Right? So when given an input that's actually of category K, we're going to get some kind of probabilistic response from the annotator. A perfect annotator is going to say K 100% of the time, but other annotators might have noise, either random noise or bias, and I'll give you some examples later. So now we know how accurate the annotators are on a category by category basis in terms of both their accuracy and their biases. And then we look at the actual data that we're generating when we actually have an annotation task. And there what we're going to have is a bunch of labels. I'm just going to call them YIJ. That's the label for the ith item by the jth annotator. And just for simplicity, some of this data can be missing, but just for simplicity, I'm not trying to do all kinds of fancy indexing in this talk. So what we're going to do is we're going to generate the annotator's label for an item Y, IJ, by looking at what the true category is and looking what the annotator's response profile is. So basically what we're going to do is we're going to say, well, what we're going to do is go on to the next slide, which I foreshadowed a bit here. I love that word, foreshadow, by the way. Thanks for reminding me in the earlier talk. So here's the start of their abstract. When compiling a patient, I probably shouldn't read this to you, but basically the idea was it was about patient record data. Right? It was about the fact that doctors, when taking people's history, would often come up with different results. And then what did you do? You got this mismatched patient record data. My wife was working with Noemi at Biomedical Informatics at Columbia and looking through piles and piles and piles of data and finding even things like smoking status was completely wrong and people misreport. So there's all kinds of measurement errors. So in general in statistics, all of this kind of stuff goes under what's called measurement error. Right? So if everybody was perfect, we wouldn't really need statistics. But here what's happening is we're trying to use this very buggy meter that is a person to try to measure what the true category is, and there's error in that measurement. The same way a scale might overweigh people by 1 pound or underweigh people, or you might get noise because you can't quite read where the dial is. So anyway, going back to our previous model, Dawid and Skene's model was particularly, I don't actually even know how to pronounce Skene's name. Dawid and Skene's model is very simple. They just take the prevalences according to a uniform distribution. They didn't actually have a prior. They did a frequentist version of this and used EM. But it works out to the same thing in a Bayesian setting, just to put a uniform prior. The reason I write it like this is I'm going to generalize it a bit later. Then the ZIs are just generated independently, categorically. So each item in the corpus independently gets a category assigned based on the prevalence distribution. Then the annotator accuracies, the annotator responses for annotator J to item K is going to get a Dirichlet distribution. That's also uniform. Implicitly, what's going on here is we're treating each annotator's response for each category as completely independent and estimating all of that stuff independently. Later, I'm going to talk to you a bit about pooling some of that data to get better estimates and sort of inferring as you go what the regularization should be. And then the only tricky bit of this is the categorical distribution of the label, right? So there what we're going to do is we're going to look at annotator J's response, theta J, to the true category ZI, and that's going to generate the label. So This model existed in 1979. These guys fitted it with EM to a bunch of data, which was kind of tough then. They said this was a very slow procedure. I've implemented their model in Java and can handle millions of annotations at the level of on the order of like a couple seconds. So computers have gotten a lot better since then. So let's look at a particular example of this to try to bring this abstract picture back to something a little more practical. So here there's a paper by Rosetsky, Shotke, and Wilbur, which I think was 2 or 3 years ago, and I have the reference, but I forgot to put it in here. What they did was they considered an ordinal response. They actually had people rate on a 1 to 7 scale how positive or how certain somebody was in saying something in a paper. So they might have said something like, we're absolutely certain we've established this result. We conjecture that we did this. We conjecture that this is not true. We have no idea what's going on. And those lead to different numbers in terms of how certain somebody was, right? So it's a 7-step grading scale there. So what we're going to do is we're going to really think about this way. We're going to decompose the annotator response into bias and noise. This is not what Rosetsky et al. Did. This is what Dawid and Skene actually do. So the Rosetsky et al. Weren't aware of the Dawid and Skene stuff when they did this. So one thing that's been interesting is since we all have the same little tinker toys in our toolbox, Andre, a number of other people in this world have gone and reinvented Dawid and Skene's model from scratch. I've seen at least 6 or 8 different papers that had no idea this stuff was out there in the epidemiology literature, but it's not surprising because we're all kind of starting with the same tools. So think about decomposing the annotator responses in this point, right? You might have an annotator who biases to the high side, right, or biases to the low side. Right, this might be easier to think about in terms of movie ratings. You might have people who give all 1 to 3 responses or all 4 to 5 responses, right? Similarly, you can think about paper reviewing, right? This model has actually been applied to that as well, where you have a bunch of reviewers judging papers and you want to combine those. You know that some reviewers are hanging reviewers and give every paper a 1 except for their student's paper or something. So you see this all over the place. You can also get biases toward the middle, which like ACL's been trying to fight against. You see this a lot in reviews too, where everybody gives a 2, 3, or a 4, and they're just kind of wishy-washy. Or you get biases toward the extremes. What's interesting about building a proper annotation model for all of this is there's a lot of information in somebody who's systematically biased. Systematic noise hurts. Systematic bias we can compensate for by modeling the annotator. So I have an example down here of a theta J response. So there's going to be on the column there's 4 possible true categories, and then along the rows you see the annotator's response. So if the true category is 1, this annotator is 70% likely to say 2. If the true category is 2, they're 60% likely to say 3. And so forth. So this is an annotator bias toward the high side. You can see reading down the diagonal, those are going to be their accuracy numbers. They're only going to be 10% accurate for category 1. But think about this information theoretically in terms of what information you can gather. If this annotator says 2, it's very likely that the true category is 1. So there's a lot of information there in what they're actually saying. So thinking about building a statistical model, you often want to say, what would I do if I had all the data? So we're often working in these missing data situations. So a standard way to start is to say, what would I do if I had all the data? Or at least what would I do if I had all the conditional data? So here, this is a very simple model, so we can actually work through it all. If the true categories are known, it's very easy to directly estimate the prevalence, right? If we know what the categories are, we can just do a very simple estimate there. Similarly, if the true categories in the annotator labels are known, it's very easy to estimate the annotator responses. Similarly, if the prevalence is known, the annotator response is known, and the labels are known, it's easy to estimate the category via Bayes' rule, and I'll work through that example, which is the critical one on the next slide, because that basically is how we adjust voting for annotator accuracy. Right? So by being able to very simply evaluate all these conditional probabilities, it's very easy to implement EM, and it's very easy to implement Gibbs sampling. But since we can write the full joint posterior down, or the full joint distribution down, it's easy to use other methods for sampling too. So first let me talk about prevalence a bit, because I'm just sort of warming up to actually working through a real example. So assuming that we have binary categories, 0 and 1, prevalence is just going to be the proportion of 1 labels here. So the RTE, the textual entailment, artificially balanced their data set 50-50. Sports articles are about 15% of all the articles if we were trying to just find articles about sports. Bridging anaphors are about 6% of all the anaphors, at least according to the data Massimo Poesio and crew collected using phrase detectives. Person named entity tokens make up about 2% of the total tokens in the MUC corpus. The tennis sense of love in Newswire is about 1 in 200. The relevant docs for a web query out of the trillion or so docs that Google says its indexes, it says it gets 500,000, but that's probably an overestimate because they have to kind of fiddle to get those. I originally made this slide for Elric. So let's look at just the gold standard estimation of prevalence first, right? So let's say we have the proportion of 1 labels and we just make that our prevalence. That's the maximum likelihood estimator there. More data always produces more accurate estimates, but the question is how much? Here it's a very simple binomial model, so we have a closed form version of this using a normal approximation that basically says the confidence interval that you're going to have, the 95% confidence interval is going to be plus or minus 2 times the prevalence times 1 minus prevalence over n. The key thing here, and in pretty much all of statistics due to the central limit theorem, is that your uncertainty always goes down with the square root of n. So to get more certainty, to get twice as much certainty, or to cut your confidence intervals in half, you need to collect 4 times as much data, right? And just to give you a feel for this, if you have 100 samples and 20 of them are positive, you estimate 20% prevalence, but that's plus or minus 8%. So the 95% interval is 12 to 28. So you're not really very certain about that, right? You want to do this kind of thing for kappa if you're doing kappa too. So what you need to do is you need to collect more data. And you need more data if the measurement of those categories is subject to noise. This is assuming in practice we don't actually know the true categories, but instead we're estimating this with noisy data. So we need to adjust for that. Luckily this EM or Bayesian model will do all of that all at once for you. So let me just show you how you calculate the category probabilities here. This is how you adjust, given known annotator responses, how you adjust something like their voting, right? So we know what the prevalence is, we know what the annotator responses are, and we know what the labels are from the annotators why, right? By Bayes' rule, we can invert probabilities. If we want to convert the probability of A given B, it's proportional to B given A times A. In other words, it's proportional to the joint probability. So how do we apply this to category probabilities? Well, the probability of the category I given the label yi, the annotator responses theta, and the prevalence pi, this is going to be just applying Bayes' rule directly from above. This is going to be the probability of yi, given all the rest of the information, times the probability of the category I, given theta and pi. Actually, theta isn't even necessary there on the right-hand side. So I reduce this in the next line to just the dependencies in the graphical model. So the first thing, the probability of the category given pi, now I've reversed the order, is just the probability of category I given pi, which is just pi subscripted with the category. And then we multiply in all the annotations. For each of the j annotators, we multiply in what's the probability that they said yij, given that the true category was ci and their response was theta. Right. Very easy formula. I don't think I need to tell you about that. So let me just go through an example of how this would work. This is a somewhat counterintuitive example, and I chose this purposely because the result disagrees with the voted result, right? So we have a prevalence of 20%. We have specificities. So we have 3 annotators, so they're organized in columns, and the specificity of the first annotator is 60%, the second one's 70%, and the third one's 80%. And the sensitivities are on the next line. And then they annotated, the annotations are that the first annotator said 1, the second annotator said 1, the third annotator said 0. So we work through all the math here, which is just from the previous slide, and we wind up getting an 11% probability that the category is equal to 1, even though 2 out of 3 of our voters said that. Even 2 out of 3 of the annotators said 1, we're estimating the probability is very low. The problem is the prevalence of one category is very low. So we start out with knowledge that 1 categories are less likely than 0 categories. And the dissenting annotator, annotator 3, you'll see has a very high sensitivity. They have a 90% sensitivity. So the chance that they're going to say 0 when the true answer is 1 is only 10%. Right? So all of that conspires to give us an 11% number as our estimate there. Right? So how can we actually apply this kind of thing in practice? Well, the simplest supervised inference scheme is that we just want to randomly sample a bunch of items to label. We label a random subset of these with truth. We then use this gold data, or what we're taking for gold data, to estimate the prevalences and estimate the annotator responses. Then when we've done that, we can use the formula from the previous slide to estimate the categories for the remaining items. This is, for instance, what Crowdflower does, the group that spun out of PowerSet and does a lot of Mechanical Turk, and now they're building into their own system. Why do we need to randomize? I just want to stress a few statistical points. It's necessary to avoid selection biases. If we select easy items, then we're going to overestimate accuracies. If we select unrepresentative items in other ways, we're going to misestimate the prevalence, and so forth. So let me go through a more of a worked example here of how the whole thing works end to end. This is from a data set that was collected in the 80s of 5 different dentists diagnosing a condition called Caries. How am I doing on time, by the way? When do I go to?
You've got about 20 minutes left. And then
Oh, great. Okay, perfect. So 5 dentists diagnosing Caries here. So the data is presented where you get the responses. So there were 1,880 cases where all the dentists said no, and they were looking at x-rays, right? So this is a typical kind of annotation problem. It's in the real medical domain, not in the text informatics domain, but this is a common sort of test set for dealing with epidemiological models of combining different annotators. And then, like, if you look at the end line, there was 789 cases where dentist 5 was the only dentist that said the person had caries. So you see this huge bias in annotator 5 toward the positive side. And these were real practicing dentists they went out. They were probably dental professors or something because it was a research study. So you can imagine the data is going to look exactly like this for any kind of binary labeling setting where you have everybody annotate all the data. In general, everybody might not annotate all the data and the shape gets a little ugly, but it doesn't really fundamentally change everything. So fitting this model in a Bayesian setting, so we basically take the model I showed you and then look at the posterior. This is the posterior histogram for the prevalences. Right? So we're pretty sure the prevalence, the mean of the posterior, which is the unbiased Bayesian estimate that minimizes expected difference from the true value, is 19.6%. The consensus estimate, where they all say 1, is only 2.5%, and the majority estimate's only 13%. Right? So we actually get a very different estimate than if we went and just voted what was going on here. Here's what the posteriors for the dentist accuracies look like. Right, so this is what theta looks like essentially, but we've only got 2 outcomes, right? So the annotator specificity is what's the probability that they're going to correctly reject a negative example, and the sensitivity is the probability that they're going to correctly accept a positive example, right? So we see dentist number 5 has a very low specificity and a very high sensitivity, as we'd expect. That is, there's a lot of cases where dentist 5 says there's caries and the other people don't agree, so they have a very low specificity. You can't trust what they said in many cases. And you can see how there's very, very different performance of the different dentists. If we're doing this fully, probability. Right, so that's the probability that you get. It's basically specificity, and the horizontal axis is just density. Right, so it doesn't really have a scale other than it's a continuous density. So that is, we're saying there that something like dentist 5 specificity is somewhere between 65% and 75%. But we're pretty sure it's centralized somewhere around 70%. Here's what the posteriors look like. You probably won't be able to read this, but you'll be able to see the shape for the different votes. Right, so let's look at one that's interesting. Like if the second one up there is just dentist number 5, if dentist number 5 says something, we're pretty sure that it's not there, right? But we get very different responses from different pairs of dentists, depending on what their sensitivity and their specificity is. If dentist 1 says there's caries, we're much more certain, still not very certain, but it's a very different response. So these are the posterior probabilities given these votes that you have of what the true category is. Do they have caries or not? So a typical way to evaluate this is to do something like a marginal evaluation. We look at, this is very commonly used in epidemiology, to use a chi-squared test on the marginals here. So we look at, there were 1,880 cases where 0 dentists said there were caries, and there were 100 cases where all 5 dentists said there were caries, and then there were all the disagreements in between. The posterior quantiles are giving you the 95% intervals as fitted by the model. So it looks like we've captured this data pretty well. Right, most of the instances there are within the predicted items, and this is still a very trivial model. So let me go on to some applications and discussion points rather than blasting you with more math as I've done in previous versions of this talk. So one question that I'm very interested in, and I think the answer is negative, is the truth out there? Right? Is it really even possible to have a gold standard where you annotate every item? That is, do all the items really have true categories? Right? The problem is that according to your coding standard, they may not. Right? There was a issue with Mach 6 that the coding standard actually defined planets as being locations. Right? They happen to have caught that in the coding standard, but and it actually was fairly determinative in the results of that because there was a single document that had a lot of instances of Mars as a location in it. But you could very well imagine that they hadn't thought about that case. Right? Or what do we do about fictional locations and so forth? So the coding standard may just be vague. So you can have all the world knowledge in the world and all the text and be a trained linguist, and you look at the coding standard and you say it just doesn't decide. It's often very hard to distinguish the author and speaker intent for an interpretation here. So for instance, reference of anaphors can often not be clear. You can say something like him, and you can get a bunch of trained linguists sit down, pore over the text, and they can come away scratching their heads and say, you know, the author just was not being very clear there. Send them to a copy editor and make it clearer. You often get issues with metonymy as well, like the difference between gene protein. When we originally started working on this, we sat down with Andrei Rosetsky and had him label data. He said, oh, this is very easy, right? Any kind of trained biologist will know for each instance in the document whether it's a gene or a protein. Right? So we printed out a couple papers and gave him a yellow marker and a green, a yellow highlighter and a green highlighter and said, okay, prove it. He gave us the first paper back and said, that was a really badly written paper. You couldn't tell for like half of them. And 3 papers later, he was like, oh, okay, this is a little harder than I thought, which is typically how things go with our customers. Our customers typically start out by saying, we want 95% accuracy. And I'm like, okay, let's see if you can get people to do 95% accuracy. And usually we back off to some more reasonable number because real data is just very, very noisy. So another point is evaluating annotators. One of the things we want to do is we want to figure out, and this was one of Dawid and Skene's motivations, not all the annotators have the same accuracy. Ideally, they'll all have high sensitivity and specificity. They will be unbiased and highly accurate. But what we want to do is we want to use these kinds of models as the annotation's progressing to provide feedback to the people who are doing this coding to help them improve their coding. We also want to filter annotators, right? And basically what we do in the previous models is we don't actually need to filter any annotators, we just need to adjust their performance. Some completely noisy annotator is going to have exactly the same response for every category. So no matter what the true category is, they're going to have the same distribution of responses. If you actually go through and work through what they're adding their annotation is to deciding what the true category is, it will just wash out. The algebra will just say, we've estimated this person to be a spammer, their code will wash out. So we don't need to go through a step of like somehow doing a hard quantization and saying, oh, this annotator is terrible, throw them out. We can just leave them in and estimate their accuracy as being really bad. The other thing we want to do for knowing how good annotators are is we might have a standard. We might want to be saying something like, well, we want 99% accuracy in our corpus. Then we can start asking questions like, how many annotators in general do we need to get to annotate an item? This is what like Ryan Snow and crew did in an early paper in EMNLP a few years ago using these kinds of models. And they basically were working with some of the crowdsource people, the Crowdflower people. So the other thing we want to do is evaluate the gold labels. We want to actually get the probability that categories are equal to 1. I was sort of talking about this on the last slide. But particularly, we want to find items where annotators are having difficulty. We want to be able to find the items in the corpus that are proving hard to annotate and either look at our annotation standard, or we can just give up and say, things really are hard to annotate. There's no way to adjudicate this thing into certainty and just accept the fact that there's going to be noise in these corpora. Usually the training methods when we build a system on this are very robust to this kind of noise. Adding in a bunch of random stuff is just going to act kind of like regularization. As long as it gets dominated by the positive stuff, it will almost always wash out of the estimates. Although this has been a topic of the last couple talks, we want to trade time for accuracy. So we want to, depending on what our goal is, right, we may be happy with a less accurate corpus. It may be better to get 1,000 items labeled very noisily than get 100 items labeled very accurately, and that may take the same amount of effort. And depending on what our goal is, one of those two outcomes may be more desirable than the other. If we want to build a corpus to evaluate systems, we might want to be very careful. But if we just want to label data to build a system ourselves, then we just want to grab the data in the way that optimizes the performance of our system in the end, and we don't really care about what the corpus quality is. That is independently of how it contributes to a system. So the other thing, getting back to kappa, is we want to evaluate the coding standard difficulty. How hard is it to actual? One thing we can do is we can look at a scatter plot of the annotator accuracies, and that'll give us some idea. But the way I originally got into this was working with Andrew Gelman at Columbia and building hierarchical models for this. So what we can do is we can actually take those priors that I wrote into Dawid and Skene's model and actually give those hyperpriors and then estimate the priors alpha and beta. The alpha and beta priors give you the prevalence prior and the annotator accuracy priors. That's going to model the population of annotators and the population of categories. So if we have multiple data sets replicated, that is, if we're doing, say, different domains, we can start estimating prevalences across those domains. Like you might have 10 different journals, right? And then say, well, in these different journals, there's different prevalences of mentions of genes, for instance. So we can actually model that to get some idea of both what the population is and what the distribution is. But by adding a hyperprior here, we can actually get parameters that characterize the population of annotators. So we'll say, what's the mean annotation like? And what's the spread? What's the variance and the skew of the distribution of annotator accuracies? With that, we can start making predictions about what happens if we just go grab a new random annotator out of the same kind of pool, right? So let me talk about some extensions and alternatives to this. One thing that I'm very excited about, which the only person I've ever seen do this is Parek Smith at Irvine in the mid-90s, worked on some annotation data for modeling craters on Venus. So it was an image labeling task, and they had, I think, amateurs, I can't really remember, go and actually look at images of Venus and circle all the craters. What he concluded was that there's no reason, and there really is no reason to do this. If you look at what a statistician would do in this case, they'd say, well, you've now developed a corpus. That corpus had some measurement error in it, right? That is, we know the annotators aren't perfectly accurate. We've done some kind of characterization of how much noise there is, right, for each of these items. We can push that noise right through our training process and right through our evaluation process. So what's typically done is the gold standard winds up being a hard classification. That is, we quantize all these probabilities that we've estimated into 0 and 1 labels, right? After we do our model, we might have something like, oh, this particular phrase has an 80% chance of being a gene reference, 10% chance of being a protein reference, and a 10% chance of not being anything. Right? But what we're going to do in that case is typically say it's a gene reference, right? But instead, what we can do is we can push those probabilities right through training. And we can also use and we get those in the model. We can also, something I'm interested in, because this was something my wife was working on with Noemi, was single annotation. She was sitting down with medical records and annotating temporal information, trying to annotate where particular medical history items, when they were recorded, and when the items in the history happened. So if somebody in the history said, I had appendicitis, they would try to figure out where it was. She was the only person doing the annotation. They had no more resources. They couldn't get anybody else to sit down and do the annotation. So what she did was, I think, quite sensible, right? She annotated the data. She built a system and then cross-validated that system on the training data. That system had fairly high performance. That gives you some indication that the data you've annotated is at least consistent, because if cross-validation's high, that means a statistical system can actually learn about the other set of the data from 90% of the data, you can learn about the other 10% of the data, right? The problem with this is that usually what you want to do is you want to do this interactively. So there's always this creeping specter of bias here. So the question is, she's looking at the output of her system. Maybe she's going to change the annotations. You can kind of artificially game the system to get good agreement. Arguably, that's what you want to do. When she was going through and doing this, what she found was that she was inconsistent on adding days of the week. Right? Sometimes she'd say Monday, September 18th, and sometimes she'd just say September 18th, and the system was actually messing up. So she went back and changed all that data to make it consistent, and the cross-validation went up. If you did this in a really cheesy way, you could just change every one of these things so that they agreed with the system and get fairly 100% accuracy. So there's some subtlety here. The other kind of thing we can do, which sort of, again, gets at some of the earlier talks we saw, is do semi-supervised inference. Right? We can include some items that actually have known categories. If the people who design the coding standards are certain about a bunch of items, we can throw those into the item pool. Right? This is very straightforward to incorporate mixed known, unknown data in either EM or Gibbs sampling or really any kind of Bayesian approach. The effect of this is it's going to sharpen all of our estimates. It's going to take our posterior intervals and shrink them, because now we've added more data which we've said doesn't have any measurement uncertainty. We could throw a little measurement uncertainty around those things if we wanted. So I think there's a lot of latitude for that in terms of getting sharper versions, because I think there usually are cases that the people designing the task are certain about. The other thing that really needs to be modeled here is item difficulty, right? It's clear, and more people have been doing this. I built a logistic regression style hierarchical model to do this when I first got into this. The problem is that you need a lot of data. Right, if you only have 2 or 3 people annotating an item, that's 2 or 3 data points. Remember that 1 over square root of n? We're very uncertain about what the actual difficulty of an item is. But basically we know our model's wrong. We're making this sort of homogeneity assumption that us as people who've sat down and annotated data know happens to actually be wrong. It's hard to estimate even with 10 annotators per item, but Becky Passano and I are now working on a word sense data as part of the mask corpus, and we're collecting 25 Mechanical Turk annotators per word instance for 1,000 instances of 50 words. And talking about Mechanical Turk not being expensive, this is going to cost about $10,000. So it's not, it's still trivial compared to the amount of time we've put into it. If you looked at our salaries, then, we still beat that. But, that's 47 words. We'd like to do 40,000 words, right? And we don't have the $50 million to do that with Mechanical Turk that it would take. But hopefully when this data collection's done, and we're on the last few words right now, we'll actually have data from which we can analyze a lot of these hierarchical properties. We can actually start getting a good model, a good sharp model of how difficult some of these items are. Becky's had this problem that all of her papers get rejected because people tend to reject this assumption when you submit a paper and say this. Right? People will say, oh, no, what are you talking about? There's a lot of people who only do this in theory, I think, and have never actually sat down with real data, and they tend to reject papers. So we're trying to get enough data that will convince anybody that there are item effects here, and that there are sense effects, so that something like one sense of a word might be very hard, or there might be 2 very confusable senses, like the word color in WordNet. There's one like physics sense of color and one perception sense of color that I seriously can't tell apart myself. Although the annotators seem to do okay because they just ignored the physics example. And that turned out to be the truth, actually, but I'm very literal and I got confused. So the problem statistically with estimating item difficulty, I should say, is that we wind up with too many degrees of freedom in the model. So to explain an error that an annotator makes on a particular item, we have two ways to do that. We can either say the annotator is not very accurate, or we can say the item's hard, right? And those two things were it's like together those two things aren't very well identified. Right? The posterior inferences all work fine, but we just don't get a very sharp notion of how hard things are. This is just more details on how we can actually do that, which I don't want to talk about. And this is the last slide that's actually got technical information on it. This is a paper I've been really taken by. Vikas Rekar at where is he at? The company that makes medical devices. I can't even remember. Siemens. Right. They built a really, really interesting model. This is a JMLR paper that I would highly recommend. This is, in my opinion, the best work that's been done on this area since Dawid and Skene. And they came up with a very, very interesting notion. They actually jointly estimate the model and the annotations. So now that you've got, the nice thing about these big graphical models in Bayesian land is they're very modular, and it's very easy to plug more information into those models. So what these guys did is they just plugged more nodes into the graph. So they basically, as they were iteratively building this model with EM, I think they used EM, but I can't remember. The details of that don't really matter. You can do it lots of different ways. What they did is they actually took the data that they were generating, used those to train a model, and then essentially took that model as another annotator, right? So it may be beneficial in this setting to use more than one. They just used a fairly simple logistic regression, but there's all kinds of interesting both practical and theoretical issues around this. One is it going to bias one thing we know it's going to do is it's going to bias your category estimates to things that are learnable, right? So it's going to kind of push your annotation scheme and your labels towards something that logistic regression can learn. Although they showed with true held out data that it actually improved properly held out data as well. So like I said, this is a very fascinating paper on this. So I think I'll stop there, and hopefully that will be enough points for discussion to keep us going. Thanks. If not, I've got like 80 more slides if you want to see more detail.
So I'm going to go towards the beginning of the talk, where you said you use some gold data. So basically, you have an individual, you individually model the annotator's response based on data, based on the prevalences and individual annotator biases, and you get these from some gold label data. That's where I kind of lost it because so you need some kind of seed gold data in order to estimate the prevalences?
No, you don't need any seed gold data at all.
So where do you get so where do you get the initial prevalences?
You know why. Y is observed. That's all that's typically like in the Dawid and Skene model for this, Y is the only thing that's observed. All these are unknown, and you just estimate everything jointly. Right, so you can do this either with EM or with Gibbs sampling or with other kind of Bayesian things. So it's a standard kind of thing to do.
And while we're on the slide, the third line. So the assumption is the response is conditioned only on the category label?
Only on the category, yes, exactly.
Okay, which is somewhat simplifying, but yeah.
How would you suggest? So I suggested improving it by the item by some kind of measurement of item difficulty. The other thing we can do is actually in these models add more effects, right? If you take this out of the kind of Dirichlet multinomial setting and you put it into a multinomial logistic regression setting, what you can do is you can start adding other predictors. So instead of just modeling the annotator's accuracy based on the identity of the annotator, you can say something like, you can have a categorical predictor and say, this is a mechanical Turker, this is a grad student, this is a biomedical expert. Right, and those might have different profiles, and we can learn those different profiles of those things if we have enough data for each of those categories and use that to help. Similarly, we can do the same thing on the item side. So we can model simply item difficulty, but then we can, in modeling the item difficulty, we can make that a regression too. We might, if we're labeling a word, we might look at the word frequency, for instance, and maybe low frequency words are harder to annotate or easier to annotate. I don't know, but there may be an effect there. Right, so we can start adding all those kinds of effects into this model. This is a very, very simplified model, so I totally agree. It's just very hard to present the math for the more sophisticated thing to people who aren't used to multinomial logistic regression models with all these random effects.
So I agreed with all your points on your kappa rant, but I guess my question would be, in your ideal world, what would we be reporting instead of kappa?
I would report, personally, I would take something like the Dawid Skene model and report the parameters.
So like all the parameters.
Yeah, basically the theta parameters, the pi
right, all the ones that
parameter. But the other thing you can do is just look at agreement. I think agreement's actually more informative than kappa in terms of the goals of actually annotating a corpus. We don't actually care about the chance adjustment, it turns out. When we're building a corpus, we're building one corpus. We usually don't care how that compares to something else that may have a harder decision problem. We care more about what the agreement is and what the accuracy is going to be as a result of that.
Can you talk a little bit more about trying to estimate the difficulty of a certain annotation task or a certain item? The types of things that you might consider measuring?
Well, the only thing that I've actually done in practice for this is not measured anything, but simply added a parameter for difficulty, right? So basically you'd wind up getting a kind of regression setting where what you would be doing, instead of saying all the items have like basically this model is assuming that every item is the same, that the difficulty is the same, that the annotator's response just depends on the annotator, right? If we put this into a regression setting, the response can depend on any number of other variables that we throw in, right? We basically build a little regression and we do an inverse logit and we get our probability back again. So for item difficulty, the only thing I've looked at is the identity of the item itself. So that lets the items vary in terms of, but I think there's any number of things you could do based on the different domains. So for like co-ref, you might measure the distance between the two, or dictionary frequency, or I've already said that one, or number of references in uniprot, or does it have, like people doing morphology, for instance, have found, does it have a Greek root or a Anglo-Saxon root to be determinative of how accurate somebody's going to be in doing the morphology for it. So I think that's going to depend a lot on a task-by-task basis, but it's basically like any other kind of machine learning or statistical modeling case. You just need to investigate a bunch of predictors and see which ones work. Although you can usually just throw them all in and let regularization sort it out. Who's going to win the steering contest? Can we just stop? Thanks.